This chapter is going to cover Chapter 8, Section 5, Part 2. The counting principles continued from yesterday. So yesterday we talked about the counting principles, the simple counting principles, how to identify if it's permutations where the order matters. And we talked about if we wanted to arrange a certain set in order, that the way we would find out the number of combinations would be n factorial, or the number of ways that it can be put in order. And then we talked about what would happen if you wanted a certain number at a time. So let's say there's 10 runners in a race and you want to know how many different ways the first, second, and third places can be done. That would be a permutation where 10 is your n and the 3 is your r. And then the formula for P and R, we talked about being n factorial over n minus r factorial. So similar to your binomial coefficient formula, except you're not multiplying times r at the end. Okay, so we're going to pick up where we left off, which is distinguishable permutations. So suppose a set of n objects has n1 of one kind of an object, n2 of a second kind, n3 of a third kind, and so on. The number of distinguishable permutations of the n objects is given by n factorial over each of the individual elements, their own factorial. So a quick example of this is if you were asked in how many different ways the letters in my last name can be rearranged. So if I had spelled out Chris Weiser, the first thing you would do is count how many initial elements there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my n is 11. And then you would look for all of the individual letters, whichever ones repeat. So C is only once. That would be a 1 factorial, so you don't really need it. H is only once. That would be 1 factorial. There are 2 R's, so I would say 2 factorial to represent the R's. There are 2 I's, so I would say 2 factorial to represent the I's. And there are 3 S's, so it would be 3 factorial for the S's. And then there's 1 W and 1 E. So while you could list each individual one, the 1 factorials don't really matter because you'd be multiplying by 1 either way. And then once you get to this point, you would want to break down that 11. So 11, 10, 9, 8, 7, 6, 5, 4, 3 factorial over 3 factorial, and then 2 times 1 and 2 times 1. I would cancel these out. Obviously, I don't have to worry about the ones, but 2 goes into 4 twice, and 2 goes into 2 one time, and then I would take and multiply out the rest of those numbers, and that's going to represent the number of possibilities created by rearranging the letters of my last name. All right, so example 9 says, how many distinguishable ways can the letters banana be written? So I want to first count how many letters are in banana. 1, 2, 3, 4, 5, 6, which means n is 6. And then there's only 1 B. There are 3 A's, and there are 2 N's. So it will be 6 factorial over 1 factorial, but we don't need it, times 3 factorial times 2 factorial. So then I do 6 times 5 times 4 times 3 factorial over 3 factorial and 2 times 1. The 3 is going to cancel out. 2 goes into 4 twice. And I'd get 6 times 5, that's 30, times 2, that's 60, times 3, that's 180. The second part, or major part of this section, is combinations. So while permutations are when the order of the objects matter, for combinations, it is not important. So for example, how many ways can letters, so not numbers, this should be letters, be taken from the alphabet 3 at a time? So if you have your entire set of 26 letters, then with permutations where it says in what order can it go, ABC is not the same thing as BCA or CAB. We would count those as 3 separate sets. But in this case, where it doesn't matter what the order is. It doesn't mention anything about order being important. We would count A, B, C, B, C, A, and C, A, B all as the same set of letters. So when you're finding the combination, this is our formula, and it should look familiar because this is the same as the binomial coefficient. So the combinations of n elements taken r at a time would be n factorial over n minus r factorial times r factorial. So if you had looked back on the example we had just done, my entire set is letters, which is 26. That would be 26 factorial over, if it's 3 at a time, it's 26 minus 3 factorial times 3 factorial. And then you would simplify it out. Example 10 says, if for A, in how many different ways can 3 letters be chosen from the letters A, B, C, D, and E, and the order of the elements is not important? So words like arranged and order are going to lend to permutations, whereas the absence of those would be permutations. So if my set, my initial sample set is A, B, C, D, and E, that means that the N is 5. And it said how many different ways can 3 of these letters be chosen from there. So my R is 3. So I would do C, 5, 3, 5 factorial over 5 minus 3 factorial times 3 factorial. And I'd get 5 factorial over 2 factorial, 3 factorial. I want to break the bigger number down until I hit the next one, which would be 5 times 4 times 3 factorial over 3 factorial times 2 times 1. The 3 factorials are going to cancel. 2 goes into 4 twice, and I'd get 10. B says a standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible where order is not important? So if you think about holding out a poker hand in front of you, the actual physical order of the numbers of the cards is not important. So if my set is 52, that means my N is 52. And I want to know how many combinations for 5 cards. That's your R. So 52 factorial over 52 minus 5 factorial times 5 factorial. This would be 52 over 47 times 5, all factorials. This 52 becomes 52 times 51 times 50 times 49 times 48 times 47 factorial over 47 factorial, and then 5, 4, 3, 2, and 1. The 47s cross out. 2 goes into 48 24 times. 3 goes into 24 8 times. 4 goes into 8 2 times. And 5 can go into 50 10 times. And then you want to multiply out what's there. So if I do 52 times 51 times 10 times 49 times 2, I get 2,598,960. So that's a lot of different hands that you can get of poker from the same set. All right, so that finishes up the notes. Quick review, some formulas from this section. The permutations is n factorial. Permutations taken a certain number at a time is n factorial over n minus r factorial. Permutations with distinguished terms is n factorial over n1 factorial, n2 factorial, and so on and so forth. And then combinations, C and R, which is n factorial over n minus r factorial times r factorial. Okay, you can use the rest of the time to work on your assignment, which is 8.5. Have a great weekend and hope to see everybody at Carnival tonight. Remember, a homework pass for coming and a second homework pass if you can dunk me in the dunk tank.